Right. So the term interferences in spectroscopy is used to describe anything that is not an analyte. So it's used to describe anything that is not an analyte, but that affects the reading on our spectrometer. That's what we call an interference. If it's not an analyte, but it affects the final reading on our spectrometer, we call that an interference. There are so many types of interferences that can be in our sample, that can be surrounding a sample, or that can be in our instrument itself. One type of interferences we have are spectral interferences. These are concerned with a specific wavelength that is put through our sample. So spectral interferences are only concerned with the specific wavelength that we pass through the sample. And how do these affect the final reading? We have what we call spectral line coincidence. This happens when whatever we have as our analyte absorbs the same frequency that is absorbed by interfering atoms, that can be absorbed by interfering ions or polyatomic ions. Remember, our sample does not only contain an analyte. There could be other compounds in our sample, there could be other atoms in our sample, there could be ions in our sample which are polyatomic ions. And these ions, if they have the same mass to charge ratio, we have to mind this, a same mass to charge ratio. If they share a mass to charge ratio, they are going to absorb the same wavelength. The same with broadband absorption. If whatever is in our sample absorbs a wide range, just like we see with hydrogen here, it absorbs this range of wavelengths. So if the wavelength we use here falls within that specific range, it may be absorbed by an interference. And what we read at the end will be falsified. It will be a false reading. What we see with spectral coincidence, there are so many types of that. In the ICP mass spectroscopy, we see what we call isobaric overlap. This is when the isotopes, remember isotopes have the same mass to charge ratio, So this is an ion isotope that matches the same mass to charge ratio as the nickel. So because they share a mass to charge ratio, they are going to absorb the same frequency. The same here works with the double charge effect. The double charge effect tells us that this twice the mass of a double charge, it's going to absorb the same wavelength as half the mass with a single charge. That's all because they share a mass to charge ratio. This is a 68 to 1. This is a 68 to 1 simple ratio. They are going to absorb the same wavelength. The same counts for polyatomic ions. So if you have a polyatomic ion that has a specific mass to charge ratio, that mass to charge ratio, if it matches that of your analyte, it's going to be interrupted by these polyatomic ions. So whatever the analyte absorbs can be absorbed by these ions. That's what we call a spectral line coincidence. So when that happens, more light here is absorbed, which will reduce the final intensity, and our absorbance will be higher than what it should have been originally. Another factor now, after these two, is what we call scattering. So these elements or these atoms in the sample, sometimes they do not absorb or emit the energy. What they do is the energy strikes them and it bounces off. That's what we call scattering. You strike the electron or the atom and it does not absorb that energy, rather it bounces off. So it hits the electron and it bounces off. It changes its direction. That's why we say it is redirected. We call that Rayleigh scattering. Why do you call it Rayleigh scattering? Because the electron is so small compared to the wavelength. It's called Rayleigh scattering. And as you can see in this formula, the scattering is directly proportional to the frequency. So higher frequencies will undergo more scattering. As you can see, it's a direct proportion. Higher frequencies are bound to be scattered, and
chemical interferences occurs when an analyte is not totally decomposed in a flame. There is less atoms present and therefore a reduced absorbance of the analyte. Ionization interferences affects group 1 and group 2 elements only. This includes barium, calcium, potassium, sodium, and strontium. This occurs only in hot flames. The energy of the flame excites the ground state atoms to ionic state by loss of electrons, resulting in a depletion of ground state atoms. And the element does not absorb the correct wavelength. Oxide formation. It arises due to the formation of stable oxide with free metal atom if oxygen is present in the flame. Thus, the emission intensity is lowered because a large percentage of free metal atoms have been removed from the flame.
In spectral interferences mitigation, we can select a different wavelength. For example, if an interference occurs at a chosen wavelength, using an alternative wavelength with minimal overlap can improve accuracy. Second, we have high resolution spectroscopy, which can distinguish close-spaced spectral lines, reducing overlapping signals. And now we have isotope selection. If an interfering species absorbs at the same wavelength as a common isotope, choosing a less abundant isotope with minimal interferences can help. And now we come to non-spectral interferences mitigation. The first one is ionization suppression. At high temperatures, some elements ionize, reducing the number of neutral atoms available for absorption. To mitigate this, we add an element with a lower ionization energy that ionizes fast, preventing analyte ionization. Secondly, we have spiking. It involves adding a known amount of analyte to the sample to compensate for matrix effects and improve accuracy. And now we have phosphate. Adding phosphate. Addition of a phosphate acts as a chemical modifier to prevent unwanted chemical interferences by forming stable complexes with interfering species. Isotope dilution, which is the last one, involves adding a known amount of an isotopically enriched version of the analyte, allowing for more precise quantification by comparing the ratio of natural spiked isotopes. Thank you.
The mitigation of these interferences is important to ensure accuracy and precision in our analytical results. It is also important in many different industries, real-life applications such as pharmaceuticals, food analysis, medical diagnosis, environmental diagnosis, and cosmetics. In pharmaceuticals, food analysis, and cosmetics, the miscalculation of contaminants due to matrix effect could be harmful for our consumers and lead to health problems. In environmental diagnosis, detecting heavy metals like mercury in our water is important, and keeping them within the normal concentrations to ensure a public health. These effects do not remain in our labs, they go out to the public. So we should ensure quality products and enhance the precision in atomic spectroscopy by eliminating these interferences. To conclude everything that has been said, different types of interferences were discussed: spectral and chemical interferences. What we can do to minimize these interferences, e.g. using separation and high resolution spectroscopy, and how important it is to minimize these interferences.
A proper addressing of these interferences will lead to more precise and accurate results, which is essential to making sure that we are all informed about the risk in each and every industry. Thank you.